right, so welcome to a presentation about OpenGL ES 3.1. I tried to prepare the slides for demo scene folks, for the programmer kind of guys, so that you could use all the techniques that I'm going to be talking about today in your next-gen mobile platform demos. Before we continue, I'd like to thank Daniel Koch from NVIDIA for technically reviewing the slides that we're about to see. Let's move on. First, a couple of words of introduction about who I actually am. So I happen to be an OpenGL ES and OpenGL consultant at a company called Mobica. I also happen to be a techie working for two working groups here in Kronos. This is OpenGL ES and OpenGL. And one disclaimer that I would like to make at this point is that this presentation is not done on behalf of any of the two entities. This is basically, just saying that it's only my views in here, and you shouldn't associate them with any of the two companies. Commercials aside, I've also happened to be a main organizer of the Weekend 2012 and 13 demo scene parties. And I also happen to be a PC coder at Elude demo scene group. There's Kierownik sitting somewhere in the room here. But the problem is I don't really get a lot of time for programming, at least didn't manage to get a lot of time recently, which means that the last production I made was in 2011, and yes, it placed second. So what I would like to talk about today is to basically present a couple of new ES 3.1 features. In general, do you guys know what OpenGL ES 3.1 is? Or should I make an introduction about that? OK, so this is a standard that was, I think, released in March. It's quite new. There's no actual hardware supporting the specification as of this very time. So look at this presentation as a mean of learning what kind of features you can start reading about, start just investigating in order so that you can actually use them in your demo. So what I would like to talk about today is there's a heck a lot of different features that made their way into the standard. So because of the time constraints, I cannot really talk about all of them. But things that I thought would be very interesting for you guys is atomic counters, compute shaders, indirect draw commands, multi-sample textures, for early deferred shading folks, and then shader image loadster operations, and finally shader storage buffer objects. If there is anything specific that you would like to hear a couple of words about during this presentation, please let me know. Is there anything that is not on the list that you would like to hear a couple of words about? I'll take that as a no. OK, let's carry on. So first feature that I'd like to talk about is multi-sample textures. Now, back in the ES 3.0 age, if you wanted to do some multi-sample rendering, the only way you could do that was by using render buffers. Now, this, of course, had a lot of limitations. So first of all, the major problem about this is that render buffers are not really textures. What that means is, well, you cannot really access a render buffer directly in your shader. This is not really possible unless you do a blit. And by blitting operation, I mean blitting from a multi-sample render buffer to a single sample texture. Now, it's all fine and dandy, but assuming that you can actually afford a blit, because this happens to be quite a time-expensive operation on a variety of platforms. If you ever wanted to probe a specific sample, like for instance, from your shader, you were quite curious as to what the contents of, 15th sample is for a given text cell, I'm sorry, but the only thing you can hear is an evil laugh. And if you happen to be curious about a location of individual samples or wanted to render to specific samples only, then I'm sorry, but it's three-dot thing. It wasn't possible back in that age. Fortunately, in ES 3, sorry, any questions? OK. So in ES 3.1, we got something that is called surprisingly multi-sample textures. And there's a couple of things that came with them. So first of all, multi-sample textures are always immutable, meaning that you need to use the GL text storage function in order to initialize them. You cannot actually say that I want my second bitmap to be of this resolution and the other bitmap to be this resolution. You actually have to follow the pattern of immutable textures. Also, if you plan to be using multi-sample textures, you cannot really use any bitmaps at all. So when it comes to texture targets that you can use for your multi-sample textures, you can use two different texture targets. So the first one is 2D multi-sample texture target. And this is in core profile. if you want to use 2D multi-sample array textures, this is only supported if GL ES texture storage multi-sample 2D array extension is supported. Multi-sample textures can't be bound to frame buffer attachment points, meaning that it's absolutely fine to render to multi-sample textures. You can use these textures to sample. You can actually sample them from within the shaders, assuming that the only filtering, the minification filtering that you are going to be using is GL nearest. And finally, the textures can be used to work with color, depth, stencil, packed internal formats, as well as integer internal formats. When it comes to sample distribution, you can use two approaches here. First, you can tell OpenGL ES that you want all the textiles to be distributed equally for all textiles in the image, and you can also ask to have the samples distributed differently for all the textiles. When it comes to definition of frame buffer completeness, this is also affected, obviously. So there is a new an error, you could say, frame buffer completeness error, that refers to two different situations. So first, the first way you can get a GL frame buffer incomplete multi-sample error is when you attach if you attach multiple textures or render buffers to a FBO, but they are both single sampled or multi-samples, or use different amount of samples. This is not possible in OpenGL ES 3.1. This holds also for the fixed sample locations, which is something that I discussed in the slide before in terms of the distribution of the samples. This property needs to be configured exactly the same way for all the attachments, because otherwise it's simply not going to work, and the only thing you'll get if you try to use such a frame buffer is GL frame buffer incomplete multi-sample. So in other words, hopefully this makes sense for you, but just to sum up, ES 3.1 is happy to render to multiple multi-sample rendered targets as long as their multi-sample specific properties match. Makes sense, right? OK. So when it comes to new stuff in SL world, we get new sampler types. So first, you have the sampler to DMS, which is the sampler that you want to use for accessing textures that are multi-sample but are bound to the GL texture to the multi-sample texture target. Then we have the sampler to DMS array, and I sampler to DMS for all the signed integer samplers that are multi-sample, and I sampler to DMS array, U sampler to DMS, and U sampler to DMS array. Of course, the array sampler types are only available if the corresponding extension is supported by the platform that you're coding here demo for. If you want to sample the texture, the only lookup functions that you can use are texel fetch. So the arguments are pretty plain. So the first one is the actual sampler that you want to access, because keep in mind that samplers are just opaque handles. Sorry. And the second argument corresponds to the location of the texel that you want to access. Then finally, the last argument is the sample index. So the first sample is 0, the second sample is 1, and so on. Of course, you can also use the texture size query functions. This is pretty basic stuff. This is really an extension of what you already had in OpenGL ES 3.0. Any questions so far? OK, no, let's carry on. So let's spend a couple of minutes looking at the API that is introduced for the feature. So if you want to initialize a If you want to initialize a 2D multi-sample texture, you use GL text storage to the multi-sample function. So the first argument is the target, so you can use two values for this. This can be either GL texture to the multi-sample or GL texture to the multi-sample array. Then you have the samples argument. This is the amount of samples that you want to use for the texture. Then you have the internal format. This is pretty basic, width, height. And the only thing that is interesting here is the fixed sample locations. You set that to true if you want all the samples to be distributed uniformly for all the textiles. Otherwise, you set it to false and leave it to the implementation to decide how many samples it wants to use for each of the textile, and so on. Of course, this is only going to, oh, sorry, OK, I made a mistake, because target needs to be GL texture 2D multi-sample for this one. If you want to use 2D multi-sample array textures, that makes sense. You need to use GL text storage 3D multi-sample. And the prototype is pretty similar, but there is one new argument in there, which is depth, which basically tells how many layers you want to use for your array texture. Something new that was introduced in ES 3.1 is GL get multi-sample FFV. This allows you to check platform-specific sample locations. So pname
must be GL sample position. Then you go with the index argument, which starts from 0 again till the maximum sample location that you want to get the location for. And then val is used as a deriv to store the the answer for your query. Of course, thing is, this is not really operating on any specific texture target or for any specific texture internal format, meaning that the values that you will get with this function only make sense if fixed sample, assuming that fixed sample locations would have been set to GL true, because otherwise, this simply doesn't make much sense. OK, last but not least, if you are interested in rendering only a subset of samples, you can control that with GL sample mask I. Again, there's two arguments in here. The first one is the index of the sample, and the other, OK, this is not the index of the sample. I'm sorry, I'm brain dead today. The thing is, has anybody ever worked with this function? OK, so what this means, this is a mask, right? So it is not limited by the specification that you can use only up to 32 samples for a texture. You can use, for instance, 64. Now, the problem about this is that because of the fact that the amount of samples is not that constrained in any way, there is a problem because GL bit filled is a 32-bit type. Now, what would happen if you wanted to say that I want only, I don't know, 40th sample to be rendered? Now, this is a problem. So what you do in here is that, this is quite difficult to explain, to be honest. Mask is a simple bit field mask that tells you which bits you want to render to. Now, this only allows you to define up to 32 samples at a time, whether they should be rendered to or not. Now, the way this was solved in the API was that you use as many GL sample mask I calls as you need, but only controlling the on-off state of the mask for the n32 bits. So for instance, if I set my index to 0 and then configure my mask to be something, only the first 32 bits would have been controlled by the call. But if I configure index to be 1, I would be telling OpenGL ES that, OK, I've already configured this on-off state for my first 32 bits, 32 samples, sorry. But now I would like to configure whether I'm interested in rendering to the next 32 samples. So this is basically, I'm not sure whether what I'm saying makes sense to you guys, but in general, if you look in the specification, it's quite crystal clear in there, so it's probably not worth to spend a lot of time on that. Right. Oh, well, sorry. OK, there we go. Yeah, OK. Any questions so far for the multi-sample textures? OK, good to go. So then indirect draw calls. So if you looked at ES3 and any extensions available for the API, you would have noticed that all the draw calls need to be explicitly defined by API calls. Now, this is all fine and dandy, but the problem is that this is often a bottleneck for multipass techniques where you, say, render something with one program, but then would like to use that in another program. Now, the thing is you need to do at least 2 different draw calls. That kind of sucks. And then another use case for that is that if your first program renders something to a buffer object, you would be interested in reusing that in another buffer, in another invocation of the program. So if we looked at that idea, would it be cool to actually be able to use your, I don't know, compute shaders or program objects to tell OpenGL what draw call you would like to follow? That would be quite nifty, at least for some of the techniques. For instance, bokeh could be implemented this way. But there's probably quite a lot of different ideas you could implement with this. Right. Another problem about the draw calls being explicitly defined by API calls is that this is a major cost. And the major cost comes from the validation. Because has anyone here ever implemented an OpenGL ES implementation or work on a driver? Now, the problem is that this is something that is not pretty obvious. But when you do a single GL draw array, GL draw elements, there's quite a shitload of stuff happening under the hood. And stuff like verification of frame buffer completeness, or whether all the textures that we are going to be using for sampling are actually complete, and so on. This takes time. And a good thing about indirect draw calls is that this is actually executed on GPU, meaning that the validation is ignored in most of the cases. But this also comes with a danger that you may actually happen to lock up your GPU if you ever try to use this in a wrong way. But let me first explain what this is really about. So OpenGL ES 3.1 introduces indirect draw calls for two draw calls. This is GL draw arrays instance and GL draw elements instance. So the arguments that you would normally pass by arguments are actually taken from a buffer object region instead. This also implies that a draw call does not really require an explicit pipeline flush, which is a good thing. Now let's look at the API for a few minutes. So this is pretty basic, right? So GL draw arrays instance. We have the GL mode, GL int first, GL size count, and GL size instance count. Everybody aware of this function? OK, hopefully, because this is quite basic. Now, the new function is GL draw arrays indirect. Now, the only argument that stays intact is GL mode, which is basically the argument that you use to define that, hey, I want to render some triangles, I want to render some triangle fans, and so on. But the new thing is this. So this might look as a pointer, but it's actually not a pointer, it's an offset. And this is important because it wouldn't really make much sense to just, instead of these three arguments, just use a pointer to point to a buffer where the arguments can be taken from. It never works this way. So indirect is an offset to a structure that is defined like this. So we have the usual count argument, instance count, and the first argument. There's also the reserved argument that must be always set to 0. Think of this as of a terminator. Now, one of the things that I would like to highlight here is the difference in types. So if you looked at the plain old draw call, there's this GL int first, which became GL uint first, meaning that you don't ever think about using negative first because these are going to wrap, and the GPU is probably not going to enjoy that very much. And then the same thing goes for instance count and the first argument. If we looked at GL draw elements, this is pretty similar. Now what we have in here is the GL mode, GL type, and again the old indirect argument. Indirect is again an offset to a structure that is defined like this. So we get the count argument, instance count, first index, base vertex, and reserved, which again must be 0. Now, thing is, there's quite a nifty new feature in here that is included, for free, which is base vertex. Now, has anybody ever worked with base vertex functionality? Come on, what's it for?
To offset in the vertex buffer.
Mm-hmm. Correct.
From DirectX.
Mm-hmm. I didn't hear that. Right. So this is something that we didn't really have in GL draw elements instance, but it's there. And something that I probably was not very clear about is that this structure must be built, as you can see in here and here, in your buffer object region that you're pointing to with the offset argument. Meaning that you can imagine a situation where you use your compute shader to, for instance, I don't know, render, that you use your compute shader to, to come up with an idea of rendering, I don't know, hundreds of quads, right? So this is something that could be achieved with indirect draw calls, where you would then store arguments like this, in a buffer object, and then use that buffer object region, for the GL draw elements indirect call, for instance. Now, there's a few things that we need to keep in mind. So first, very important stuff is that if you want to use this functionality, you need to bind your buffer object region to a new binding point, which is GL draw indirect buffer. This is used for feeding argument data to an indirect draw call. Now, one thing to note at this point is that some of you might be curious whether multi-draw functionality is supported in OpenGL ES 3.1, and the answer is unfortunately no at this moment. OK, so a few things to still keep in mind is that structure fields must be tightly packed, so don't ever think about, I don't know, padding the arguments or aligning them in any way. This is not required and is going to blow your GPU. Then indirect offset must be 32-bit aligned. This is quite funny because it's very, very easy to forget about that. And it could work on one driver, but would not work on the other one. So this is something that is really important to keep in mind. Then, something that I've already said, right? So buffer object must be bound to the binding point when you make an indirect draw call. Indirect is never, never, never a pointer. And then last but not least, this I hope makes sense, bound buffer object must not be mapped into process space, because obviously you cannot do something like, well, okay, I'd like to keep the buffer object mapped, and then I will just modify this nth argument, and then can my indirect draw call work? No, it won't. Okay, before we proceed with atomic counters, any questions? Yes.
Is there something like multi-draw arrays?
Say again, sorry?
Is there something like multi-draw arrays?
No, unfortunately not. So you can only make a single indirect draw call, but you can at least make it instanced. Okay, atomic counters. So this is again something new that was never made available in OpenGL ES 3.0, but has made its way into OpenGL ES 3.1. This is atomic counters, and atomic counters is something that allows you to access unsigned integers in a synchronized manner, and load and store operations are supported. Now, the way this works is that your counters are backed by a buffer object that is bound to an index binding point or binding points, because you can use multiple counters at the same time. Each counter takes exactly 4 bytes, which is the size of an unsigned integer. Right. So if you looked at atomic counters from GLSL perspective, you would notice a few new things. So first thing is that there's a new language that you use to declare the atomic counters, and it's built like that. So your atomic counters are uniforms, but you also have to qualify them using layout qualifiers. So there's 2 properties that you should always keep in mind when defining and trying to access atomic counters, which is binding and offset. So each counter is assigned a specific offset of a buffer object region by describing its binding, whereas binding corresponds to the binding point index. So think of this like, do you know the GL bind buffer base and GL bind buffer range functions? This is something that you should be using for configuring the associations. And then apart from binding, you also have to describe an offset from which the counter starts. So in this case, this is like saying that, okay, my atomic counter is backed by a buffer object that is bound to second buffer binding point, if you count it from 1, at offset of 20 bytes. So which qualifiers are needed? Are both qualifiers required to be declared at the same time or not? So there are 3 or 4 rules that you need to follow in here. So by default, offset of 0 is assumed. You need not declare offset every single declaration of an atomic counter. If you don't, the offset that you used for previous atomic counter declaration is going to be increased by 4 bytes. However, when it comes to binding, it must be explicitly stated for each declaration. So there we go with an example, right? So you have 3 atomic counters, which is Batman, Robin, and Catwoman. These all are legal, meaning that, okay, so the first atomic counter is using a binding of 3 and an offset of 4. The second atomic counter is using the same binding, but there is no offset, so this is going to be 8. And then finally, the last atomic counter uses a binding of 1, but the offset is still bumped up by 4. Thing to keep in mind is that your offsets must not be shared. You cannot do something like use the same atomic counter declaration that is pointing to the same region of the buffer object. This is bad, and it's not going to work. Okay, so the thing about atomic counters that might not be obvious is that they work as samplers, meaning that these are all opaque handles that you cannot really access. You need to use a dedicated API in GLSL in order to extract the value or decrement or increment. And the API is quite plain. So there are 3 new functions that you should be using for altering or messing with atomic counters. This is atomic counter decrement, which decrements the counter value, whereas the counter is passed as an argument, and then returns that very value. Then we have the atomic counter increment, which returns the counter value and then increments it. And finally, you can always check the value of the atomic counter by calling, hey, guess what, atomic counter. Okay, last but not least, operations will be wrapped to a very specific 32-bit range. So for instance, if you set the atomic counter to OXFFFFFF and then increment that, this is going to wrap to 0. It's not going to be clamped in anything. Right. OK, so as with any new API, there are some caveats. Well, after all, what would a coder's life be without gotchas? So if we looked at the related minimum maximums in OpenGL ES 3.1, you would notice that hey, it's quite OK, because in my compute shaders, I can actually use up to 8 atomic counters backed by at most 1 buffer object. Now, that's all good and fun. But anything that you are worried about at this point, you should be, because for other stages, it's not so fun. Do you know the idea of minimum maximums in OpenGL ES? So, OK, let me elaborate on that a little bit. The thing is, I know this sounds very weird, but if you look at OpenGL or OpenGL ES specification, there's this GL max set of properties. These tell you that, OK, that's the largest amount of something that I can use in my application. Now, the idea of minimum maximums in this spec is that all platforms, all implementations of OpenGL or OpenGL ES that are conformant with the specification and describe themselves as, hey, I'm an OpenGL ES implementation, must meet these constraints. I mean, the values that they return must be at least as specified. They can be larger. Now, as you can see in this example, this is actually quite sad because, OK, I can use atomic counters in compute shader. This is guaranteed to work. But what about these? Now, this is not fun because this means that atomic counters are not required to be supported for fragment or vertex shader stages, which is, well, depressing. I'm not a hardware vendor, so I cannot really answer that question, but there's a good news in here. The good news is that NVIDIA's Tegra K1, which is, I think, going to be released in Q2, will have the same limits as their desktop hardware, which is quite OK. But then for other lower mid-end platforms, this is not guaranteed to work. So well, just keep that in mind. This is very important, because when coding your demo, you may assume that, hey, well, atomic counters must work in fragment or vertex shader stages, but apparently, no. OK, before we carry on with compute shaders, any questions, apart from the one that was already asked that I cannot answer? OK. Let's move on then, what the time is. OK, cool, we've got half an hour left. OK, so we need to speed up a little bit because it's like I'm behind the schedule. OK, so compute shaders. So this is something that the desktop peeps are already aware of, but this is completely new stage introduced in OpenGL ES 3.1. This sits outside the regular rendering chain and is totally focused on data processing, meaning that you do not really get any varyings. You cannot feed the compute shaders with attributes that change with the vertex that is being processed for the specific invocation. No, instead, compute shaders work very similarly to how OpenGL would work, or CUDA, or anything. This is just ported, the idea ported to OpenGL ES. So apart from the fact that you actually need to sample specific texture locations or images and such, you also need to keep in mind that anything that you come up with in your compute shader must be stored using images, SSBOs, etc. There is no GL position that you set it. There we go. But then, yeah, something that could be raised at this point is that, hey, we have OpenGL, WTF, right? Well, the thing is, if you ever tried to work with OpenGL and OpenGL at the same time, you'd have noticed that there is something like interop, which is, I think, described by acquire and release functions. And these come with a very sad feature, which is pipeline flush, meaning that this is quite expensive. When you compute something in OpenGL and want to use it in your OpenGL world, you actually need to tell OpenGL that, hey, there's this resource of OpenGL that I would like to use, so can you please make sure that this is that all the data within that container is computed before I can actually use it in in my shader. This is very time expensive, and any kind of a barrier is always a problem. So you want OpenGL ES to be responsible for for this synchronization, right? This is something that we achieve with compute shaders because it's one API that is responsible for synchronizing stuff. Now, another thing is code portability, meaning that you can reuse functions that you use in other shaders for computing stuff, for extracting data from any objects like, as I said, images, SSBOs, and such. Right, so how do they work? Now, this is, so as I already said, there is no thing like, I don't know, GL vertex ID or specific mean of telling, so which invocation am I really executing at this time? Instead, compute shaders operate in two embedded workspaces. You have the general global workspace, which you could treat as, I don't know, like text cells in your picture, or blocks. That's a better example. You've got blocks in your compressed image, right? The block is 4x4. And then you have local workspace, which consists of invocations that can communicate with each other and that can be responsible for processing that very block. So this might not be clear at a first glance, but I'm probably not doing the best work at explaining stuff. But in general, global workspace is built of work groups, and each work group consists of work items. Now, thing to keep in mind is that work items can synchronize. They can operate on the same data, assuming that you take care of making sure that these invocations are actually synchronized, that we are not operating on the same data from different invocations. There's also quite a lot of caveats with compute shaders that I will be discussing in slides to come. When it comes to size of workspaces, the size of global workspace determines amount of work groups that you want to execute, and size of local workspace determines amount of invocations per single work group. So for example, if your global work group size was 16 by 8 by 64, and your local work group size was 128 and 11, then you would get a total of 1 million something invocations. So that's quite a lot of invocations, but bear in mind that these are not really executed in parallel. The way they are run is that there's a couple of rules that are adhered to when it comes to compute shaders. So work items in one work group can be run in parallel because if your platform is not capable of running as many threads as needed at the same time, they will be serialized in one way or another. So we cannot really assume that they will be always run in parallel. But at least this can happen. So your work items can actually use barriers to synchronize. So are you guys aware of what barriers are? Because this is something that I haven't yet described. OK, so I'm not going to elaborate on that. Finally, as I said, data exchange is supported for work items. This is achieved by so-called shared variables. Of course, you cannot just write something to a shared variable and then read it from another invocation, because this is not guaranteed to work. You need to actually put a memory barrier within your shader to make sure that all invocations execute up to this point, so that after the barrier, you can actually extract the data from a different invocation. Last but not least, workgroup execution order is totally non-deterministic. You are not allowed to make any assumptions at all, because if you do, this may work on your very computer, but will not work on somebody else's, and that's probably not fun when you're striving to meet the deadline. API-wise, there are two ways to kick off compute shaders. The easiest way is to use GL dispatch compute. This takes 3 arguments, num groups x, y, and z, and this describes global workgroup size. When it comes to defining local workgroup size, you use a special language in your shader, which is layout, local size x, y, and z. By default, these properties take a value of 1. So if you, for instance, we could totally ignore local size z, because this would be automatically assumed to be 1. Another way to launch a compute shader is using an indirect dispatch call. This is called GL dispatch compute indirect, and surprisingly, it takes only 1 argument, which is indirect. And the argument describes an offset at which the arguments, num groups x, y, and z start. So offset is relative to the buffer object, that region that you bound to GL dispatch indirect buffer binding point. And it also needs to be aligned to a 32-bit boundary. When it comes to local workgroup size, it doesn't really change. You use the same language as on previous slide. OK, ES 3.1 specific constraints. So again, the SAD minimum maximums come here into play. We've got the GL max compute workgroup count, which is the maximum number of workgroups that you can spawn. This is 65K. Then you have GL max compute workgroup size, which is 128 by 128 and by 64. This is maximum local size of a workgroup. And then this is GL max compute shader memory size, shared memory size, which is 16K, meaning the maximum storage size of all shared variables. OK. Load store operations. Any questions for the compute shaders? Yeah, no, OK. OK, so this is something that I consider to be quite a very nifty feature in OpenGL ES 3.1. So this is images. So have you ever worked with images? No. OK, so let's look at this way. So consider a single map of an image that makes up a texture object. So this could be a cube map face, a single layer of a 3D texture, or a slice, or whatever. What images allow us to do is to we can now use shader invocations to actually modify texture data. So this is quite interesting, really, because up to now, the only thing that you could have done from your shaders was to use render targets to render fragments, right? That was cool, but often not really required. So what we now can do is to use special API in GLSL that allow us to say, hey, OK, I want this specific texel to be this from now on. Of course, this is not for free, as you will see. But nevertheless, let's focus on the API for the time being. So before you can actually use an image in your shader, you need to bind it to a so-called image binding point. This is something totally different than texture units. These two are not, the amount of image binding points can and probably will be different from the amount of texture units that you can use in your application. So if you want to bind your image, you use GL bind image texture API. This is quite complex if you look at it. So there's quite a lot of arguments in here. The first one is unit, which is the index of an image binding point that you want to use. The second argument is the texture object ID that you will be modifying one of the, layers, faces of. Then we have level. Level is surprisingly the map level of the object. And then there's this layered argument. Now, this has got nothing to do with layered rendering. This is really, this tells you whether you want to have access to all layers of the texture within your shader or not. So if you set layered to false, you'll need to make sure that value that you pass to the layer argument makes sense, because if you are not using multiple layers of a texture, you actually need to tell OpenGL ES which layer you want to be able to read or write to. And then there's this access argument. This tells whether you want to be able to only read from that slice, from that face or whatnot, or whether you also want to write into it. Then finally, we get the format, which tells what is the data layout of the object that you will be accessing. Right, so we've got RGBA 32F, 16F, and 32. There's quite a lot of it, so I'm not going to be reading that. But as you can see, this is quite powerful. Right, last but not least, something that I didn't say so far is that you can actually use this API to perform a simplified on-the-fly data conversion, but this is a bit more complex, and I'm not going to be dwelling into that in this slide deck. OK, so how do you actually use the images in GLSL? So images, again, just like samplers, are opaque handles. So we get new types that define the handle. So this is image2D, II image2D, or UI, UU image2D. So this is like with samplers, right? So this is used for non-integer data. This is used for signed integer images. And finally, we get the UImage2D, which is for unsigned integer images. There is no default precision. OK, I'm just going to skip these, really. But as you can see, you can use images for 2D textures, 3D textures, cube map textures, and 2D array textures. There is no default precision defined for any of these image types, meaning that you have to take care of that precision high P sampler time, image type before you actually can access the data defined by the image. But if you look at these types, you can notice that there is no way to actually tell, hey, OK, so the data that I'll be probing is in, RGBA 32F type. So you actually need to use a special layout qualifier when defining an image to tell OpenGL ES what format the underlying data is using. So this is pretty plain. I don't think there's much reason to dwell into this. From GLSL, if you want to read your images, you use image load. Pretty basic, right? So the first argument is the image type, and then the other argument is the exact textile location that you want to be loading meaning reading. Now, one catch here is that if you look at the cube map images or 2D array images, there's this thing. This is IVEC3. So can you guess how these can be used to access? For instance, if you wanted to access a specific face of the cube, how would you use this? This is pretty weird. OK, so the first two arguments define XY location of the texel, and the third argument, in case of cube map textures, cube map images, sorry, this define face index. I think that the order is plus x is 0, minus x is 1, plus y is 2, and so on. This is in the spec. And into the array, the first two components is, again, xy location of the texel, and then the third component corresponds to the layer index of to the array texture. When you want to do a store operation, you use a image store. Again, this is very simple. The only new argument in here is data, which is what you want to have written in the image. OK, so while we're at it, of course, you can, again, check the size of an image, use image size. Hey, not really surprising. At this point, is there anything you're worried about? You should be. OK, probably not. Well, as I said, there are no real guarantees as to the order in which the invocations are going to be executed, and this goes both for any of the stage. Sorry, never mind. Sorry, I didn't say anything. Thing is, you cannot assume that it's going to be only vertex shaders that are executed at first, and then this is going to be followed by fragment shaders, because these can be interleaved. Furthermore, the implementation is allowed to make certain optimizations when it comes to rendering. So this is something that I enlisted in here. So first of all, your vertex shader may be executed more than just once for each unique vertex. This can be for both implementation-dependent reasons, and one of the examples is that your vertex shader is allowed to be invoked only once per element. So if you do a GL draw elements call, and you reuse the same index for various invocations, your vertex shader is allowed to be only invoked once for that particular index. This can really backfire when you're coding something and need to meet the deadlines. When it comes to number of fragment shader invocations, this is even funnier, because you are never allowed to make an assumption that, hey, my fragment shader is going to be always executed once per sample. This is actually possible, but if you use per sample shading, which is, again, a new feature in OpenGL ES 3.1, but I'm not going to be covering that today. Then a couple of examples of what happens to fragment shader invocations is that, for instance, your OpenGL ES is allowed to perform early per fragment tests, like depth test, for instance, and if the implementation determines that the fragment is not really important, it is allowed to discard the instance, meaning that it's not going to actually invoke the fragment shader for that specific texel. And then fragments that are not contributing to the frame buffer, like for instance, if you first rendered a back face and then the front face, the back fragment is allowed not to be computed at all. Right. So if you really need all the invocations, make sure to use the per sample shading. But bear in mind that the fragment shader is not guaranteed to be always executed owing to these two bullets. If they do not really affect you, you will get one fragment shader invocation per sample. However, if you don't really need that, the number of invocations of a fragment shader is guaranteed to be somewhere between 1 and n samples, where n samples corresponds to the amount of samples that you are rendering to. Right. OK, ordering issues are one thing, but there's even something funnier, which is synchronization issues. If you look at how OpenGL and OpenGL ES used to work, in like a couple of years ago, you would have noticed that it's only API calls that can actually alter stuff, that can modify the textures that are later accessed from your shaders or from the API. This meant that the implementation was absolutely fine to inject the synchronization wherever needed. So for instance, if you first rendered to a render target and then tried to extract that data with, I don't know, get text image, the OpenGL knew that, hey, I need to flush the pipeline at this point, and then it is OK for me to handle the get request that the user has just made, meaning that what you got was basically, your call was blocked until the GPU actually processed the prior request. Now, with images, this rule is really broken because your shaders are allowed to, but do not really have to, first write to an image into arbitrary locations at any stage of the pipeline, potentially many times in a single invocation. This is even funnier because you can imagine an invocation of any of the two shader types where you first write data to a certain text cell and then try to read this from a different invocation. Now, bearing in mind the ordering issues, you are not really guaranteed that the data that one invocation has modified is going to be easily accessible for another invocation. Then another rule that is broken is that you are allowed to read from an image that has been modified earlier at any time, potentially by a different invocation. This all means that you, as a programmer, need now to worry about making sure that the invocations are correctly synchronized. Right. Something that I haven't mentioned yet is that API calls operating on assets modified by store operations can also be made right after a dispatch draw call is made. Meaning that if you looked at the example that I've made a minute ago about the rendering to render target and then doing a get text image call, the get text image call needs to know that it actually needs to wait till all the image store operations have finished executing. And without a barrier, it is not really possible. Yeah, so all in all, this is not really fun. And if implementations were to track all these store operations, this would be a heck of a lot of expensive. So the question here is, what can we really do to help ES at this point? I need to speed up. I've got 7 minutes left. Jesus. OK, so if you wanted to inject a memory barrier, you would use a GL memory barrier call. There's a lot of bits to choose from. So just an example, you have the GL texture fetch barrier bit, meaning that well, this note is important. The bits refer to operations made after the barrier. So for instance, if you wrote in your shader to an image and then wanted to fetch the texture to which you had written, you would use this GL texture fetch barrier, because this flushes all the operations that will affect texture fetching process. I don't really have time, so I cannot really discuss the other 2 bits, but this is all specified in the spec. This is something totally new, not available in OpenGL, so I'd like to talk for a minute about that. This is a lightweight by region barrier, which synchronizes read-write operations done by prior fragment shader invocations, given that the region subsequent invocations will operate on. Meaning that, for instance, if you render a quad that is not really taking a like whole screen space, and your subsequent fragment shader invocations will also operate on that very region, you can use GL memory barrier by region. Now, the difference between the two is that this function will only synchronize all read-write operations performed on that very particular region, instead of synchronizing operations for all the text cells of your render target. So, for instance, this would have worked miracles for a deferred renderer, whereas would not work for all the, for instance, texture gathering-based techniques, because this could actually try to access text cells that are outside the region that you will be rendering to. Again, region size is implementation dependent, but it's allowed to be 1 pixel, meaning this could backfire on your, as I said, texture gathering implementations. And this, again, only works for fragment shader invocations. OK, when it comes to API-based memory barriers, this is a GLSL barriers. So we've got a couple of those. So memory barrier just synchronizes everything. This is the least sufficient memory barrier that you can probably only use for debugging purposes. You do not want to use that all the time because this is inefficient. Then you have memory barrier atomic counter, which flushes all the atomic counters, makes sure that the caches are refreshed. Memory barrier buffer, which flushes your buffer variables and for images. And then you also have memory barrier shared, which flushes your shared variables. Something that is only available in compute shaders is group memory barrier. This synchronizes your your variables that are shared between workgroup instances. OK, there's also quite a few layout qualifiers that you can use for your images. So we've got coherent keyword, which is about if you use images in more than just a single stage, you want to use this keyword because this will effectively say that something that I've written to an image can then be read from a subsequent stage. So for instance, in a vertex shader, if I wrote to an image, I want to make sure that I will be able to read that value from a fragment shader. Then we have volatile, which is a keyword that tells that, OK, my image is the only mean of accessing the data in an image. There's not like, I don't know, it is guaranteed that no other thing will interfere with the value that I will be able to access with my image. Then we have restrict keyword, which is, oh, I think I mixed these two. OK, sorry, I was talking about restrict, Jesus. No other variable points to range accessible by the qualified image. And volatile is about underlying value that can't be changed at any point during execution by other invocation. Then we have read-only and write-only. This is pretty basic. So read-only says that the image can only be used for read operations, and write-only says that the image can only be used for store operations. The meaning for this is quite simple. This is about optimizing stuff. So without these keywords, the compiler is not really allowed to make any assumptions, meaning that it will take the slowest route possible just to make sure that stuff stays in sync. OK, min-maxes. Again, this is pretty sad story. So you've got zero images guaranteed to work in vertex shader stages, 0 images guaranteed to work in fragment shader stages, but at least this is going to work always for compute shaders. Hey. OK, when it comes to image units, you're guaranteed to have up to 4 image units. And the combined amount of images that you are allowed to use in all your shader stages is 4. This could be, of course, higher, but this is the min-max. I'm not sure if we have. Can we extend the presentation or not? OK, I need to skip this then. I'm sorry. This would have taken too much time. You made it. Do you have any questions? OK, no, so thank you for attending. It was a pleasure. Hope you learned something. Thank you.